In RF and AC circuits, signals are constantly changing with time. If we try to analyze them directly in the time domain, the equations quickly become complex and difficult to manage. In this lesson, we will learn phasors and how they transform oscillating signals into simple rotating vectors for easier RF analysis. In AC and RF systems, electrical signals such as voltage and current are not constant. They continuously vary with time in a sinusoidal manner. This time-varying behavior makes direct analysis using standard algebra difficult because every operation must consider both amplitude changes and time dependence simultaneously. If we attempt to analyze circuits using only time domain equations, we often end up solving differential equations that become increasingly complex as the circuit grows in size. This approach is mathematically correct, but not efficient for engineering work, especially in RF systems where multiple sinusoidal signals interact at different phases. Phasors were introduced to solve this problem by transforming time-dependent sinusoidal signals into time-independent representations. This allows engineers to focus on magnitude and phase relationships without constantly tracking time variations. A phasor is a complex number that represents a sinusoidal signal in a simplified form. Instead of describing a signal as a function of time, a phasor captures its amplitude and phase as a single rotating vector in the complex plane. In this representation, the length of the vector corresponds to the signal's amplitude, while the angle represents its phase relative to a reference. The time variation is implicitly contained in the idea that this vector rotates at a constant angular frequency. This means that a phasor is not the signal itself, but a compact representation of a sinusoidal signal's steady-state behavior. It allows engineers to move from a dynamic time-based description to a static geometric representation that is much easier to analyze mathematically. Phasors are directly based on Euler's formula, which connects complex exponentials with sinusoidal functions. Using this relationship, a sinusoidal signal can be rewritten as a complex exponential expression where the oscillation is represented as rotation in the complex plane. Instead of working with sine and cosine separately, engineers can use a single exponential term to represent both components simultaneously. The phasor then becomes the constant part of this expression, while the exponential term represents rotation over time. This separation of time-dependent and time-independent components is what makes phasor analysis so powerful in RF engineering. It reduces complicated time-varying equations into simple algebraic relationships. One of the most important advantages of phasors is that they transform differential equations into algebraic equations. In the time domain, capacitors and inductors introduce derivatives and integrals into circuit equations, making analysis more difficult. When using phasors, these time-dependent operations are replaced by simple multiplication with complex numbers. This allows circuits to be analyzed using techniques similar to DC circuit analysis, even though the system is actually operating in AC. As a result, engineers can apply familiar tools such as Ohm's law, Kirchhoff's laws, and network theorems directly in the frequency domain, greatly simplifying the analysis of complex RF systems. In RF engineering, phasors are essential because they provide a practical way to analyze real-world signals that vary sinusoidally with time. Almost every RF system, including antennas, filters, amplifiers, and transmission lines, relies on phasor-based analysis. Impedance, which includes both resistance and reactance, is naturally expressed in phasor form. This allows engineers to evaluate how signals behave when they pass through different circuit components and propagation environments. Without phasors, RF circuit design would require significantly more complex time domain calculations, making system design slower and less intuitive. Phasors are therefore a foundational tool in both theoretical analysis and practical RF engineering. In this lesson, we learned that phasors are a powerful way to represent sinusoidal signals as rotating vectors in the complex plane. They transform time-varying signals into steady-state representations, making circuit and signal analysis much simpler and more intuitive. In the next lesson, we will explore logarithms in engineering and understand why RF systems often use logarithmic scales instead of linear values. If you found this useful, like the video, subscribe, and follow for the next lesson.